Mars looks dead, frozen, red, silent. But last month, a space camera caught something that rewired everything we thought we knew. A scar 800 miles long, carved in a single day by the most violent flood in solar system history. We will follow that flood from the moment the ground cracked open, to a hidden ocean, to a secret reservoir of liquid water still sitting miles underground right now. We will ask the question scientists are afraid to answer out loud. Was Mars ever alive? If you enjoy the journey, like and subscribe. Let us begin. A camera orbiting Mars sent back an image in May of 2026, and the scientists who opened it went quiet. They were looking at a wound, a gash across the surface of Mars so massive, so clean, and so violent that it took a moment to understand what they were seeing. 800 miles of carved rock, a channel wide enough to swallow a small country, and it had been hiding in plain sight for billions of years. The European Space Agency's Mars Express orbiter took the image using a camera called the High-Resolution Stereo Camera. This instrument maps terrain in 3 dimensions, building a picture of elevation, depth, and shape. When the full image came together, what appeared was one of the most dramatic geological features ever recorded in our solar system. The feature has a name, Shaalbatana Vallis. It stretches from a region called Xantha Terra near the Martian equator and runs northward for 800 miles until it empties into a vast lowland plain. To put that in terms you can feel, 800 miles is roughly the distance from New York City to Chicago, and this entire channel was carved in a geological instant. On Earth, rivers take millions of years to cut through rock. The Colorado River spent about 5 million years carving the Grand Canyon. Shaalbatana Vallis was gouged through solid Martian rock in what scientists estimate was a single catastrophic event. One moment, one rupture, one flood so powerful, it reshaped a planet. The channel runs 6 miles wide at its broadest point. That is wider than Manhattan Island is long. And in certain sections, the walls drop 500 meters straight down. Standing at the rim of this canyon would feel like looking down from a height 3 times taller than the tallest skyscraper on Earth. The bottom would be invisible in shadow. What made scientists pause was not just the scale, it was the shape. The channel had curves and branches you only get from moving water. There were carved streamlines in the rock, places where water had spun in massive whirlpools and ground the walls smooth. There were teardrop-shaped islands of rock that water had flowed around, just like you see behind boulders in a fast-moving river. Every detail in the image screamed one thing. Liquid water moved through here, fast, and in a volume that is almost impossible to picture. Mars today has an average temperature of -80 degrees Fahrenheit. Its atmosphere is so thin that exposed liquid water would evaporate almost instantly. There is nothing on the surface right now that could produce a river, let alone a flood of this scale. So where did all that water come from? That question is what drove scientists to dig deeper into the data. And what they found beneath the surface of Mars changed the story completely. Because the flood did not start at the surface, it started underground. Deep underground, in a pressurized system of water and rock that had been building for a very long time. The geology of the channel tells a story of something enormous failing all at once. A pressure that built for millions of years and then found a crack. And when it found that crack, it did not leak. It exploded. What triggered it, and how much water we are really talking about, is where the story gets bigger than anyone expected. Stand at the edge of Shaalbatana Vallis in your mind for a moment. The ground drops away 500 meters in front of you. The walls are vertical, sharp, and raw. The rock layers are exposed like a sliced cake, each stripe of color representing a different era of Martian history. Below you, the canyon floor stretches 6 miles across, wide enough to fit the entire width of Chicago from one wall to the other. And this canyon runs in a nearly straight line for 800 miles, in every direction you can see. The Grand Canyon in Arizona is 277 miles long. Shalbatana Vallis is nearly 3 times that. The Grand Canyon reaches a depth of about 1 mile at its deepest point. Shalbatana Vallis reaches depths of over 1,600 feet in carved sections, and its walls are sharper, less eroded, more violent in their geometry. But size alone does not tell the full story. What makes this feature genuinely stunning is what the shape reveals about the speed and force of the water that created it. When scientists look at river channels, they read the rock like a book. The curves of the channel show the direction of flow. The smoothness of the walls shows how long the water was present. The teardrop formations, called streamlined islands, show where the water split around obstacles and accelerated. Shalbatana Vallis has all of these features, and every single one points to the same conclusion. This was carved by a flood moving at extreme speed, carrying enormous amounts of sediment and rock, all at once. Scientists call this kind of feature an outflow channel. Mars has others, but Shalbatana Vallis stands out because of how well preserved it is. The Martian atmosphere is so thin and dry that erosion happens very slowly. The channel carved 3.5 billion years ago still looks almost as sharp as the day the water stopped. The rock walls have barely weathered, the streamlined islands still stand with clean edges. It is like a crime scene that was sealed the moment it happened and opened only now. The camera that captured all this used stereo imaging, meaning it shot the same terrain from 2 slightly different angles, and combined the images to produce a 3-dimensional model. Scientists could measure exact depths, slopes, and shapes. They could calculate, based on those shapes, the approximate speed and volume of the water that carved each section. The numbers that came back were staggering. The volume of water required to carve this channel in the estimated time frame exceeded anything ever recorded in Earth's geological history. Every flood event humans have ever measured, including the ancient megafloods that carved parts of the American Pacific Northwest, would have been a trickle by comparison. And yet the channel is just the scar. It is the wound left on the surface. The real story is what caused it. Because the water that carved Shalbatana Vallis did not fall from the sky, and it did not flow gently from a melting glacier. It came from beneath the ground, from a system so pressurized and so massive that when it finally broke open, the planet cracked. Understanding how that system built up and why it failed when it did means going underground into the hidden plumbing of early Mars. Most people picture a flood as rain, heavy rain, rising rivers, water spilling over banks. That kind of flood is measured in feet. The flood that carved Shalbatana Vallis was measured in hundreds of miles of destroyed rock. To understand how something like this is even possible, you need to picture Mars 3.5 billion years ago. The planet still had a thicker atmosphere, temperatures were warmer, and underneath the surface, a massive system of groundwater had been locked inside porous rock for tens of millions of years. Porous rock works like a sponge. Water seeps into the tiny gaps between rock particles and gets trapped there. On Earth, this kind of underground water is called an aquifer, and we drill into aquifers every day to pull up drinking water. On early Mars, these underground aquifers were enormous. They stretched for hundreds of miles, buried under layers of dense rock. The key ingredient that makes this relevant is pressure. The deeper underground water sits, the more rock presses down on it from above. That pressure squeezes the water and keeps it from escaping. But geothermal heat, the heat coming up from the planet's hot interior, kept this water warm enough to stay liquid even at great depth. So you had a massive body of warm, pressurized water sitting beneath the thick rock ceiling, unable to go anywhere. For millions of years, nothing happened. The rock held. The pressure built. Then something changed. Scientists believe the surface in the Xanthi Terra region was compromised. The overlying rock weakened, either through ancient asteroid impacts fracturing the crust, or through volcanic activity heating and destabilizing the layers from below. The ceiling of the underground reservoir developed a critical fault, and when the pressure inside exceeded what the weakened rock above could hold, the water did not seep out. It erupted. The technical term for this event is a groundwater outburst. The pressurized water blasted upward through the fractured rock with enough force to carry massive chunks of the crust with it. The eruption point was not a small crack. It was a zone covering dozens of square miles where the ground simply gave way all at once. The water that surged out was moving faster than any river on Earth. It carried rock fragments, soil, and ice. It slammed into the surface terrain and immediately began cutting downhill, following the slope of the land northward. Every second, the flow was carving deeper into the rock beneath it, using the debris it carried like sandpaper on a massive scale. This process, where a flood uses its own carried material to grind away the rock it moves across, is called abrasion. And in the first hours of the Shalbatana Vallis flood, abrasion was happening at a rate that would be catastrophic by any scale we can imagine. The flood did not slow down over time. The gradient of the landscape funneled it faster. The channel it cut became a guide rail, focusing the flow and increasing its speed. For a period scientists estimate lasted days to weeks, this torrent of water, rock and debris surged northward for 800 miles. And when it finally arrived at its destination, something even bigger formed. But to understand the destination, you first need to understand what the eruption left behind at the starting point, because what the ground looked like after the water left is one of the strangest landscapes on Mars. The flood was the explosion. The underground aquifer was the bomb. To understand how Mars stored that much water beneath its surface for so long, you have to think about the planet as a machine, not a dead rock, but a system with moving parts, internal heat, and geological pressure. 3.5 billion years ago, that machine was running hot. Mars has a core made of iron and rock. Like Earth's core, it radiates heat outward through the planet. This geothermal heat, rising through layers of rock, creates a zone beneath the surface where temperatures stay warm enough to keep water liquid even when the surface above is frozen. Scientists call this zone the subsurface habitable layer, and on early Mars, it was enormous. Here is how the trap worked. Water, whether from ancient rainfall, melting ice, or volcanic steam, seeped down through cracks in the surface rock. Over millions of years, it moved slowly, working its way deeper and deeper until it reached the zone where geothermal heat kept it warm. There it pooled inside porous rock, filling every tiny gap and cavity. As more water arrived from above and the rock sealed over time, the water had nowhere to go. The pressure inside that saturated rock layer grew steadily, year after year, century after century. Think of it like squeezing a water balloon under a heavy book. The water wants to escape, but as long as the cover holds, it stays put. The cover in this case was kilometers of solid Martian crust sitting on top of the aquifer. Scientists can estimate the size of this ancient aquifer by measuring the volume of rock that was removed during the flood. The channel carved by the outburst had a calculable volume. The debris deposited downstream had a measurable mass. By working backward from these numbers, researchers determined that the underground reservoir held an almost incomprehensible amount of water. The entire system, the water, the porous rock, the sealing crust above, stretched for hundreds of miles across the Xantha Terra region. And it was not just sitting there passively. The geothermal heat underneath was actively keeping it pressurized, like a slow-burning engine running continuously for millions of years. What makes this especially significant is that scientists now know this kind of underground water system did not disappear when the surface dried out. Evidence from Marsquake measurements shows that a version of this system still exists today, buried much deeper, still liquid, still pressurized. The modern reservoir sits between 7 and 13 miles underground. The ancient system that fed the Shalbatana flood was shallower, closer to the surface, which is why it was vulnerable to breaking open. The moment the crust above it cracked, all of that stored energy released at once. The pressure that had been building for millions of years found a way out, and it did not trickle. It detonated. What came after the eruption, in the area directly above the broken aquifer, was a landscape so alien and so chaotic that it has its own geological name. And the shape of that terrain tells the story of the flood's origin point better than any instrument ever could. That landscape is still visible on Mars today, perfectly preserved exactly as the water left it 3.5 billion years ago. Every great disaster has a moment of no return. For Mars, that moment happened 3.5 billion years ago, somewhere in the region we now call Xantha Terra. The underground reservoir had been building pressure for millions of years. The rock above it had been holding. And then, in an instant, it stopped holding. Scientists have traced the origin point of the Shalbatana Valley's flood to a specific location, the interior of a large ancient crater called Orson Welles. Named after the famous American filmmaker, this crater sits at the head of the channel like a broken valve at the top of a pipe. And in the images captured by the Mars Express orbiter, the floor of that crater tells a story of violent structural collapse. The crater floor does not look like a typical impact basin. On most craters, the floor is relatively flat, possibly with a central peak from the impact. The Orson Welles crater floor looks shattered. It is broken into massive blocks of rock, separated by deep cracks and sinkholes. The surface dropped in multiple places, leaving a jagged, uneven terrain that looks like the ground was pulled from underneath. That is exactly what happened. When the pressurized water beneath the crust finally found a weakness in the rock above, it did not just leak through. The water pressure was so extreme that it blasted upward through the fractures, with enormous force. As the water evacuated from the underground reservoir below the crater, the rock above it lost its support. With nothing holding the ground up from below, gravity took over. The surface collapsed. Thousands of square miles of Martian crust dropped downward into the empty space left by the escaping water. The result was a terrain that geologists call chaotic terrain. And chaotic is exactly the right word. Imagine taking a concrete floor and removing everything below it. The concrete sags, cracks, tilts, and breaks into irregular slabs. Now imagine that happening across an area larger than the state of Connecticut, with slabs of rock hundreds of feet thick, dropping different distances depending on how much water had evacuated beneath each section. Some blocks dropped straight down, others tilted at sharp angles. Some areas collapsed completely into deep pits. The whole zone became a maze of raised platforms, shattered ridges, and empty basins. This collapse happened fast. Scientists estimate the ground failure occurred over a period of days, maybe weeks, as the water continued to drain from beneath. The blocks that dropped are still visible today, preserved in the Martian cold, exactly where they landed billions of years ago. And while the crater floor was collapsing inward, the water that had been released was already moving. It surged out of the crater zone and onto the surrounding terrain, immediately cutting northward down the slope of the land. The flood had begun. The combination of collapsing ground and surging water created a starting zone of total geological chaos. Nothing in the crater region survived intact. The rock was shattered, displaced, and rearranged in ways that took scientists years to map and understand. But the chaos at the origin point was just the opening scene. Downstream, the flood was doing something even more dramatic to the rock it was moving across. There is a type of landscape on Mars that has no real equivalent on Earth. Scientists call it chaotic terrain, and when you see it in the Mars Express images, your brain struggles to process it. The ground looks like it was shaken violently, cracked into enormous pieces, and then partially swallowed. Some blocks of rock stand tall like isolated towers. Others tilt at steep angles, leaning against each other. Between them are deep pits and trenches that drop into shadow. This was created entirely by the underground flood, when the pressurized water beneath Xantha Terra blasted its way to the surface. It evacuated the underground reservoir that had been supporting the ground above. Think of a table with thick legs. Remove the legs, and the tabletop crashes down. The Martian crust was the tabletop. The water-filled rock below was the legs. When the water left, the surface had nothing to rest on. But the collapse did not happen evenly. Some areas above the aquifer lost their support faster than others, depending on how quickly the water evacuated from each section. This uneven collapse is what created the maze-like appearance of chaotic terrain. Some blocks dropped 10 feet, others dropped 300. Some tilted, some split down the middle. The result is a landscape that looks like a giant hand reached up from underground and scrambled everything. The chaotic terrain around the Orson Welles crater covers an area of roughly 80 square miles. That is larger than the entire city of San Francisco, and every square inch of it was formed in a geological window of days to weeks, not over millions of years. What makes this feature scientifically valuable is that it acts as a fingerprint. Wherever you find chaotic terrain on Mars, you know a groundwater outburst happened directly below that spot. Scientists have mapped multiple zones of chaotic terrain across the Martian surface, and each one marks an ancient flood origin point. The planet is covered in these fingerprints, each one the scar of a forgotten catastrophe. The chaotic terrain at the head of Shalbatana Vallis is among the largest and best preserved examples on the planet. Because Mars has so little weather and almost no liquid water on the surface today, these ancient landscapes erode extremely slowly. The blocks of rock that collapsed 3.5 billion years ago still stand in roughly the same positions they fell into. In the Mars Express images, scientists can identify individual blocks the size of city blocks, tilted at angles, surrounded by collapsed pits. They can trace the fault lines where the ground cracked. They can see exactly where the water escaped and where the ceiling came down. But here is what makes this even stranger. Beneath the chaotic terrain, the underground reservoir that once held all that water is now empty. The cavities left behind, the spaces where water once filled porous rock, are now just voids in the Martian crust. Dead chambers where a pressurized sea used to be. Or so scientists assumed, because when researchers started looking at other parts of Mars, at the deep crust far away from Shalbatana, they found something that changed the question entirely. The water did not all escape. Somewhere deeper, a reservoir was still waiting. That discovery would come billions of years later. First, the flood had somewhere to go. A filmmaker who once convinced millions of Americans that Martians had invaded Earth now has his name on the place where Martian water escaped in the most violent outburst the planet ever produced. The Orson Welles crater is roughly 55 miles across, sitting in the Xanth Terra Highland region, near the Martian equator. It was formed by an ancient asteroid impact billions of years before the flood. The impact shattered the ground, fractured the crust, and left behind a basin with a compromised floor. That fractured floor would become one of the most important geological features in Martian history. When the underground aquifer below Xanth Terra began building pressure, the weakened floor of the Orson Welles crater was the path of least resistance. Pressurized water seeks cracks the same way air leaks from a punctured tire. The crater's fractured base gave the water exactly the weak point it needed. The images from Mars Express show the crater floor in remarkable detail. Mapped in 3 dimensions, it reveals a surface covered in the signature shapes of chaotic terrain. Blocks of rock stand at irregular angles. Deep collapsed pits dot the floor. Fractures run in every direction. The entire basin looks like the moment after an implosion, with everything that used to be solid now broken and rearranged. Scientists have confirmed that the primary outflow of the Shalbatana Vallis flood originated directly from this crater. The channel begins at the northern rim of Orson Welles and extends outward from there in a clean, high-speed path. The geometry of the flood's starting angle, the direction of the carved streamlines, and the distribution of debris downstream all trace back to this single point. What is remarkable about the Orson Welles crater's role is that the impact that created it likely happened hundreds of millions of years before the flood. The crater sat there, fractured and quiet, while the underground aquifer slowly filled below it. Then, when the pressure finally reached its breaking point, the ancient crater became the exit point for one of the most violent geological events in solar system history. This kind of delayed interaction between an ancient impact and a later flood event is something scientists are now looking for elsewhere on Mars. If one fractured crater floor could act as the trigger point for a massive outburst, other craters might have done the same. The planet may have experienced multiple events like this, each one leaving a channel, a chaos zone, and a downstream basin. The name Orson Welles carries a particular weight here. Welles broadcast a radio drama in 1938 describing a Martian invasion of New Jersey, complete with fake news reports of cities being destroyed. It caused genuine panic across parts of the United States. People believed Mars had attacked Earth. The reality turned out to be almost the inverse. Mars was not attacking, Mars was collapsing. Its own underground water was tearing the planet apart from inside. And the evidence of that self-destruction, carved in stone and preserved in cold, is still spreading outward from the base of that crater today. But what happened to all that water once it left the crater zone? Where did 800 miles of raging floodwater actually go? The answer involves an ocean, ancient shorelines, and a basin that swallowed everything. When the floodwater surged out of the Orson Welles crater and onto the open terrain of Xanth Terra, it did not slow down. It accelerated. The land north of the crater slopes downhill toward the great northern lowlands of Mars. Gravity pulled the flood in a single direction. And as the water moved, it began doing something that seems almost impossible. It carved rock faster than most geological processes move in 1 million years. The walls of Shalbatana Vallis, in the sections where the flood ran deepest, drop 500 meters from rim to floor. That is roughly 1,600 feet. To picture that, stand at the top of the Empire State Building. Now imagine doubling its height and looking straight down from that point to the ground. The base of the channel walls sits at that depth. These walls are steep, in many places nearly vertical. On Earth, canyon walls this sheer would normally be rounded and softened by millions of years of rain, wind, and temperature changes. The walls of Shalbatana Vallis are sharp. They have texture. You can see individual rock layers in the Mars Express images, each layer representing a different period in Martian geological history, each one cut cleanly by the passing water. The mechanism that carved these walls so quickly is called hydraulic plucking. Fast-moving water, especially water carrying large amounts of rock debris, creates rapid pressure changes against the channel walls. These pressure changes literally pull chunks of rock away from the wall face. The rock does not erode gradually, it breaks away in pieces, sometimes in blocks the size of houses, which then get swept downstream and used to carve further sections of the channel. The flood was essentially using Mars against itself. The rock it tore from the walls became the tools that cut deeper walls further downstream, a self-feeding demolition machine that ran for hundreds of miles. In the narrower sections of the channel, where the walls converged, the water would have been moving even faster due to the compression. Scientists estimate that in these constriction zones, the floodwater moved at speeds comparable to a fast highway, carrying debris, boulders, and rock fragments. Anything in the path of that flow was destroyed. The floor of the channel also shows evidence of enormous whirlpool activity. Circular depressions called potholes, formed by spinning water grinding into the rock below, are visible in the three-dimensional terrain maps. On Earth, potholes form slowly in rivers over thousands of years. The potholes in Shalbatana Vallis formed fast in the days or weeks of active flooding because the rotational forces involved were far beyond anything a standard river produces. After the flood ended and the water drained away, the channel stood exactly as the water had left it. No rain came to soften the edges. No vegetation grew to stabilize the slopes. The cold, dry Martian atmosphere simply preserved everything in place. 3.5 billion years later, a camera floating in orbit captured every wall, every pothole, every carved layer, and sent the images back to Earth. And somewhere at the bottom of all those images downstream, at the end of 800 miles of carved rock, was where the water finally stopped, where it collected, where it sat long enough to leave one more signature on the planet. That signature is a drowned landscape the size of a continent, and its story is even stranger than the flood that created it. 800 miles of water racing across the surface of Mars had to end somewhere. It ended in Chryse Planitia. In English, that name means the Golden Plain. It is a massive lowland basin in the northern hemisphere of Mars, sitting well below the average surface elevation of the planet. It is, essentially, a bathtub, and the Shalbatana Vallis flood filled it. Scientists have been studying Chryse Planitia for decades. Multiple spacecraft have landed in or near this region, including the Viking 1 lander in 1976. But the significance of this basin as a flood destination has come into sharper focus with the new terrain mapping from Mars Express. The geometry is undeniable. The Shalbatana Vallis channel runs directly into Chryse Planitia, like a river emptying into a bay. The slope of the terrain guides every drop of water from the Orson Welles crater straight down into this basin. And in the basin itself, geologists have found the physical evidence of what happened when the water arrived. The floor of Chryse Planitia shows sediment patterns that match what you would expect from a massive flood entering standing water. When fast-moving water-carrying sediment hits a body of still water, it slows down instantly. The sediment it was carrying drops to the bottom in a specific pattern called a delta fan. Scientists have found these delta fans at the mouth of the Shalbatana Vallis channel, where it enters Chryse Planitia. The fans cover an area of roughly 80 square miles. Delta fans are significant for one specific reason. They only form in standing water. A river flowing across dry land does not create a delta fan. The water has to enter a lake or ocean for the sediment to drop in that pattern. The presence of these fans at the flood's endpoint is direct physical evidence that a body of standing water was already present in Chryse Planitia when the flood arrived, or that the flood created one quickly enough for the pattern to form. Either way, water pooled here, in volume. Scientists estimate that the combined water from multiple ancient outflow channels, not just Shalbatana Vallis, but others that also emptied into the northern lowlands, may have created an ocean covering much of Mars's northern hemisphere. This hypothetical ancient ocean is sometimes called the Paleo Ocean, and the water depth in Chryse Planitia at its peak may have reached hundreds of feet. For a period of time 3.5 billion years ago, an ocean sat on Mars. Ships could have sailed it, if anything had existed to sail. The ocean did not last forever. Mars was already losing its atmosphere, and once the atmosphere thinned past a critical point, the surface water had no protection. It began to evaporate into space, slowly at first, then faster. What did not evaporate froze, and what froze eventually sublimated, converting directly from ice to vapor and drifting away. The ocean was gone, but not all the water followed it. Some went somewhere else entirely. Oceans leave marks. Even after the water is gone, the shoreline stays. On Earth, ancient shorelines appear as elevated ridges of sand and gravel, terraced steps carved by wave action, and bands of water-deposited sediment running parallel to where the coast once sat. Mars has versions of all of these features, and in the terrain around Chryse Planitia, scientists have spent decades mapping them. The concept of ancient Martian shorelines is one of the most debated topics in planetary science. Some researchers have argued for years that the smooth boundary between the southern highlands and the northern lowlands of Mars represents the edge of an ancient ocean. Others have pushed back, pointing to inconsistencies in the elevation of these potential shorelines. The new terrain data from Mars Express has added important clarity to this debate. In the areas surrounding the mouth of Shalbatana Vallis, researchers have identified specific elevation contours that align with what a shoreline would look like. if a large body of water had sat at a stable level for thousands of years. These contours are not perfectly flat across the entire basin, because the Martian crust has shifted and warped over billions of years. But when scientists apply corrections for the known amount of crustal deformation that has occurred, the adjusted shoreline elevations become remarkably consistent. Wave erosion patterns are also visible in some sections. Rock faces at certain elevations show horizontal cutting that matches what waves do to a coastline over time. The cuts are shallow and parallel to each other, nothing like the vertical cuts left by the flood itself. These horizontal patterns appear at the same elevation where the sediment bands and delta fans also concentrate. The combination of these features, the sediment layers, the delta fans, the corrected shoreline elevations, and the wave-cut rock faces, builds a case that something very close to a real ocean occupied this region. The water was not just a temporary puddle from the flood, it persisted long enough to reshape the coast. Exactly how long the ocean survived is still an active area of research. Some models suggest it lasted tens of thousands of years. Others suggest it could have endured for millions. The atmosphere of early Mars was thinner than Earth's but thicker than today, and scientists are still calculating how fast evaporation would have proceeded under those conditions. What the shoreline evidence confirms is that this was a stable feature, not a flash flood that came and went in a week. The water sat. It had time to interact with the rock. It left a permanent record. And in a shoreline that has been sitting undisturbed on a cold, dry planet for 3.5 billion years, the rock layers are pristine. Every sediment layer deposited in that ancient ocean is still there, perfectly ordered, like pages in a book that no one has touched since it was first written. Inside those sediment layers, scientists believe there may be one more thing preserved, something far more fragile and far more significant than rock. But to get to that, we need to follow the water inward, toward the strange dark material sitting in the center of the valley floor that appeared in the new images and immediately caught everyone's attention. Sediment does not lie. Every layer of material that settles to the bottom of a body of water carries the story of how it got there. What was in the water? How fast the water was moving, and how long it stayed still. For geologists, a sediment record is a geological diary, and the sediment at the bottom of Chryse Planitia is writing something remarkable. When the Shalbatana Vallis flood surged into the northern basin, it carried an enormous load of material, rock fragments, dust, mineral particles, and whatever else had been ripped from the walls of the channel over 800 miles were all suspended in the floodwater. The moment that fast-moving water hit the standing water of Chryse Planitia, it slowed abruptly, and when water slows down, everything it was carrying drops to the bottom. The heaviest particles, boulders and coarse gravel, dropped first and settled closest to the flood's entry point. Finer particles travelled farther into the basin before dropping. The finest dust settled last, spreading across the widest area. This pattern, called graded bedding, is one of the most reliable indicators in geology that a body of standing water received a large rapid influx of material. Scientists studying radar data and surface observations from various Mars orbiters have identified exactly this pattern in Chryse Planitia. The sediment distribution matches graded bedding from a high-energy flood event entering standing water. The coarser material sits near the Shalbatana Vallis outflow point. The finer material spreads progressively farther into the basin. On top of the flood deposit, there are additional layers, thin, finely sorted layers that look like what you would find at the bottom of a calm lake, where material settles slowly over time. These layers suggest the basin remained a stable body of water long after the initial flood ended. The water calmed down. Dust blew in from the atmosphere and slowly settled. Mineral particles precipitated out of the water as it evaporated and concentrated. All of this created a record that shows not just a flood, but a sustained body of water. There is one more layer type that is especially significant. In some sections of the basin floor, scientists have detected the presence of minerals that only form in the presence of liquid water over extended periods. These are clay minerals and specific types of salts that require water to act on rock for thousands of years to develop. Their presence in the lower sediment layers of Chryse Planitia means the water was there, it was real, and it lasted long enough to chemically alter the rock beneath it. The sediment record is essentially a court of evidence. Each layer is a witness. The graded bedding confirms the flood. The fine lake bottom layers confirm persistence. The chemically altered minerals confirm duration. The verdict: Mars had a real ocean in its northern hemisphere, and it stayed long enough to change the chemistry of the rock it sat on. What lives in ocean sediment on Earth? Fossils, preserved biology, chemical signatures of life. And that possibility is exactly why scientists are paying very close attention to those ancient layers in Chryse Planitia. But before we get to the life question, there is something sitting on the valley floor right now that nobody fully expected to find. After the flood ended and the ocean receded, Mars went quiet. The surface dried. The water either evaporated into the thinning atmosphere or soaked back into the ground. For millions of years, Shalbatana Vallis sat empty, a massive carved scar running across the Martian landscape with nothing moving through it. Then the volcanoes woke up. Mars is a volcanically active world, or at least it was for a long time after the flood. The planet has some of the largest volcanoes in the solar system. Olympus Mons, the biggest, stands about 3 times taller than Mount Everest, and the volcanic systems that fed these massive structures were connected underground to networks of magma channels that ran across the planet. Some of those magma channels ran beneath or adjacent to Shalbatana Vallis, and at some point after the water dried up, lava began flowing into sections of the valley floor. The lava did not refill the channel the way the water had. Water moves fast and cuts everything in its path. Lava is thick and slow. It pooled in the lower sections of the channel, filling the deepest depressions, spreading across the floor in a slow, heavy layer. Then it cooled. When lava cools, it contracts. As it shrinks, the surface buckles and folds under the stress of the contracting material below. These folds create patterns in the rock called wrinkle ridges, long parallel lines of slightly raised and compressed lava surface that run in curving patterns across the valley floor. They look, from above, like the surface of a brain with long folded ridges separated by shallow valleys. The Mars Express images of Shalbatana Vallis show these wrinkle ridges clearly on the channel floor. They are distinct from the rock walls carved by water. The walls have vertical cuts and horizontal sediment layers. The floor has these long, smooth, folded ridges running in curves across the lava surface. The presence of lava in the valley floor is important for a specific reason. It tells scientists something about the timing of events on Mars. The lava arrived after the water was gone. That means the volcanic activity that produced this lava was happening during a later period in Martian history, when the surface was already dry and cold. Mars's interior was still generating enough heat to push magma to the surface, even as the planet was dying on the outside. This combination, a dry, cold surface above and a still active volcanic interior below, has implications for the question of underground water. Geothermal heat from volcanic systems beneath the surface could have continued to warm deep underground water long after the surface ocean evaporated. A warm underground environment, isolated from the freezing surface, could theoretically persist for an extremely long time. The lava in the valley also trapped something underneath it. In places where the lava flowed over older sediment layers, it sealed those layers beneath it like a lid. Whatever was in that sediment before the lava arrived is now protected from the surface environment, potentially preserved exactly as it was. But the lava is just one of the surprises the valley floor holds, because sitting in the deepest, most sheltered part of the channel is something that looks completely different from anything else in the valley. And it caught the attention of the imaging team the moment it appeared in the data. In the center of the Shalbatana Vallis channel, surrounded by ancient carved rock walls and hardened lava, there is a patch of dark material. It stands out immediately in the Mars Express images. Everything around it is reddish-brown, the characteristic color of oxidized iron that gives Mars its name. But this patch is deep blue-black. It sits in one of the lowest sections of the valley floor, pooled in a depression perfectly contained by the surrounding terrain. Scientists identified it as volcanic ash. Ash is the fine particulate material ejected from volcanic eruptions. When a volcano erupts explosively, it sends columns of gas and pulverized rock into the atmosphere. The heavier particles fall back quickly near the eruption site, but the finest ash, particles so small they are nearly invisible to the naked eye, can be carried by wind for hundreds of miles before finally settling. On Mars, the atmosphere is too thin to carry ash as far as it would travel on Earth, but wind still moves material across the surface. The prevailing wind patterns in the Shalbatana region appear to have funneled volcanic ash from distant eruption sources directly into the valley. Because the valley sits below the surrounding terrain, it acted as a collector. The ash drifted in and had no way to drift back out. The blue-black color comes from the composition of the ash. Fresh volcanic material on Mars, before it has been oxidized by long exposure to the atmosphere, retains its dark basaltic color. The fact that this ash is still dark, after potentially billions of years in the Martian environment, suggests it was either deposited relatively recently in geological terms, or the valley's sheltered position protected it from the weathering that would normally oxidize and redden it. The ash patch sits preserved in the valley the way sediment settles to the bottom of a still pond. Gravity pulled it to the lowest point. The surrounding walls sheltered it from wind erosion, and the cold, dry Martian atmosphere kept it intact. What makes this geologically interesting goes beyond the color. Volcanic ash carries chemical signatures from the eruption that produced it. The mineral composition of the ash can tell scientists which volcanic system it came from, how explosive the eruption was, and approximately when it occurred. Analyzing ash deposits is one of the most powerful dating tools in geology. The ash in Shalbatana Vallis has not been directly sampled. No rover has visited this region. All the analysis comes from spectral imaging, where orbiting instruments measure how different wavelengths of light reflect off the surface material, and use that data to identify minerals. The spectral data confirmed the dark patch matches the signature of volcanic basaltic ash. But there is an interesting detail buried in the spectral readings. Some of the mineral signatures in the ash patch overlap with signatures also found in areas where water and rock interact chemically. This could mean the ash settled on a surface that was still slightly damp when it arrived, or it could mean the ash has been chemically altered over time by trace amounts of water vapor in the atmosphere. Either way, the ash is sitting directly on top of older sediment layers in the valley, layers that were deposited during the flood and the post-flood lake period. And directly below those sediment layers is the carved bedrock of Mars. The history of an entire planet written in stacked layers, sitting at the bottom of a valley that started with the most violent flood Mars ever produced. And below all of it, deeper than the ash, deeper than the sediment, deeper than the bedrock, something is still moving. When the floodwaters tore through the Shalbatana Channel at full speed, they did not destroy everything. Some sections of rock survived. They were harder than the surrounding material. The water split around them rather than over them, cutting channels on both sides, while the resistant rock in the center remained standing. Over days and weeks of flooding, the water carved deeper and deeper into the softer rock on either side, while these harder sections held their ground. What was left, when the water finally drained away, were standing platforms of rock surrounded by deep carved channels on all sides. Scientists call these features mesas. On Earth, mesas are flat-topped hills left behind by erosion, common in the American Southwest. In places like Monument Valley in Utah and Arizona, you can see clusters of sandstone mesas standing alone on a flat plain, remnants of rock that resisted erosion while everything around them wore away. The mesas of Shalbatana Vallis formed through the same basic principle, but on a much faster timescale. and at a far greater scale. Where Monument Valley mesas took millions of years to emerge, the mesas in the Martian Channel were shaped in days to weeks by the catastrophic flood. The Mars Express images show these mesas in striking detail. They stand at various heights, some reaching hundreds of feet above the surrounding channel floor. Their tops are flat, preserved at the same elevation as the original pre-flood terrain. Their sides drop away sharply where the floodwater undercut the surrounding rock. Some are surrounded by the hardened lava that later filled the channel floor, making them look like isolated towers rising from a dark plain. The teardrop shapes of some mesas are particularly telling. When fast water flows past an obstacle, it creates a specific erosion pattern. The upstream face of the obstacle gets directly hit by the current and takes the brunt of the hydraulic pressure. The downstream side sits in a lower pressure zone where the water flows around the obstacle and rejoins in a tapering stream. This creates a shape wider at the upstream end and narrower towards the downstream end, like a teardrop pointing in the direction of water flow. Scientists can read the teardrop mesas in Shalbatana Vallis like compass needles. Their pointed ends all face the same direction, toward the northern lowlands, toward Chryse Planitia. Every mesa points to where the water went, a billion-year-old record of a single day's catastrophe written in rock geometry. The height of the mesa tops also tells a story. By measuring how high above the current channel floor each mesa top sits, scientists can calculate how much material the flood eroded from the surrounding terrain. The difference between the mesa top and the carved valley floor represents exactly how deep the water cut into the rock on either side of each standing platform. In some areas of the channel, this difference is hundreds of feet. The flood carved that deep in what geologists consider an almost instantaneous event. And standing on the tops of those mesas, if a rover ever reached them, would offer a view that no instrument has yet provided. A panoramic view from the original pre-flood surface elevation, looking down into a canyon that did not exist before the water came. Below those mesas, beneath the carved floor, the rock continues downward for miles. And in the deepest part of that rock, far beyond what any current rover or lander could reach, something completely unexpected was waiting to be found. Mars had everything. 3.5 billion years ago, it had liquid water on its surface. It had active volcanoes pumping gases into the air. It had a thicker atmosphere than it does today, one that created enough pressure to keep water from instantly boiling away, and enough warmth to prevent the surface from being a frozen desert. Then it lost its magnetic field, and when it did, the sky began to bleed away. Earth has a powerful magnetic field generated by its molten iron core. This field wraps around the planet like an invisible shield, deflecting a constant stream of charged particles that flow from our star. These particles, collectively called the solar wind, are energetic enough to strip atoms from the top of an atmosphere and send them flying into space. Earth's magnetic field blocks them. Without it, Earth's atmosphere would slowly erode away. Mars had a magnetic field early in its history. The evidence is preserved in the oldest rocks on the planet, which retain traces of ancient magnetic alignment, proof that a global field once existed. But Mars is smaller than Earth. Its interior cooled faster, and as the core solidified, the engine that generated the magnetic field shut down. Scientists believe this happened roughly 4 billion years ago, a few 100 million years before the Shalbatana Vallis flood. So when the flood occurred, Mars was already losing its protective shield. The process of atmospheric erosion had already started. After the flood, the erosion accelerated. Without the magnetic field to block the solar wind, charged particles hit the upper atmosphere and knocked atoms loose. Oxygen atoms were particularly vulnerable. They were stripped away faster than volcanic activity could replenish them. The pressure of the Martian atmosphere dropped steadily over millions of years. As the pressure dropped, something critical changed for liquid water. Water can only remain liquid within a specific range of pressure and temperature. Below a certain pressure threshold, called the triple point of water, liquid water cannot exist at all. Below that threshold, water skips the liquid phase entirely. Ice sublimates directly into vapor without ever becoming liquid. Mars passed below that critical pressure threshold somewhere between 3 and 2.5 billion years ago. After that point, any liquid water exposed to the surface immediately converted to vapor and escaped into space. The ancient ocean of Chrysoplanitia did not drain. It evaporated directly into the sky and drifted away, atom by atom, over millions of years. The surface Mars today is the result of this process run to its end. Average surface pressure is less than 1% of Earth's. Average temperature is -80 degrees Fahrenheit. There is nothing on the surface that liquid water can do except disappear. But the story did not end at the surface, because some of that ancient water never reached the surface in the first place. It stayed underground, deeper than the flood could reach, deeper than the evaporation could follow. And when scientists developed the technology to peer into the deep Martian crust using seismic waves, they found something that should not have been possible: liquid water. Still there. In August of 2024, a team of scientists published a paper that forced a fundamental revision of what we know about Mars. They had been analyzing data from an instrument called the Seismic Experiment for interior structure, a seismometer placed on the Martian surface by the InSight lander. This instrument was designed to detect Marsquakes, which are natural tremors caused by the shifting and settling of the planet's interior. When a Marsquake occurs, it sends seismic waves through the planet in every direction. These waves travel at different speeds through different types of material. Dense solid rock slows them one way, fractured rock slows them differently, and liquid water slows them in a very specific and identifiable way. The scientists were examining a set of seismic events that produced waves traveling through the deep Martian crust. When they analyzed the travel times and wave behaviors, they found something unexpected in the data. At a depth somewhere between 7 and 13 miles below the surface, the seismic waves were behaving as if they were passing through a layer of saturated rock with liquid water filling all its pores and cracks. The signature was unmistakable. Geologists use the same technique on Earth to locate underground water reservoirs and oil deposits. The physics of how seismic waves change speed and character when they pass through water-saturated rock is well understood. When the Mars data produced that same signature, there was only one conclusion that fit the evidence. There is liquid water inside Mars, right now, today. The reservoir sits far deeper than any Mars mission has drilled or sampled. 7 to 13 miles of solid rock separate the Martian surface from this water layer. Current technology cannot reach it. No drill ever sent to Mars has gone more than a few feet into the surface. The size of the reservoir is extraordinary. Scientists estimated the total volume of water in this deep zone and found it comparable to the entire volume of water locked in the Antarctic ice sheet on Earth. If that water was somehow brought to the surface and spread evenly across Mars, it would cover the entire planet under a layer of water roughly half a mile deep. This water has been there for a very long time. Scientists believe it is largely the remnant of the same ancient groundwater system that fed the surface water billions of years ago. After the surface ocean evaporated and the atmosphere thinned, the deep water was simply too far underground to be affected. The geothermal heat from Mars's still warm interior kept it liquid. This discovery immediately changed the conversation about Mars in two ways. The first, Mars is wetter than anyone had assumed. The planet looks bone dry on the surface, but underneath, it is hiding more water than most scientists thought existed on the entire planet. The second, and far more significant, liquid water at depth, warmed by geothermal heat, isolated from radiation and the cold vacuum of the surface, is exactly the kind of environment where life might survive. The question of whether something is still living in that deep reservoir is one that current technology genuinely cannot answer. And the story of how scientists are even thinking about reaching it is where the stakes of this entire discovery become very real. 7 to 13 miles of solid rock. That is the distance between the Martian surface and the liquid water layer scientists detected with seismic waves. To understand how far that actually is, consider this. The deepest hole humans have ever drilled on Earth is the Kola super-deep borehole in Russia. Scientists drilled for 24 years. They used the most advanced drilling technology available, and they reached a depth of about 7.5 miles before the project was abandoned because the heat and pressure at that depth destroyed every drill bit they sent down. They barely touched the top of where the Martian water layer sits. The Martian reservoir begins at roughly 7 miles deep and extends down to around 13 miles. The entire range is below anything any spacecraft has ever reached on another planet. Mars landers have scratched the surface. Rovers have drilled a few inches. The InSight lander's heat probe, designed to drill about 16 feet into the Martian soil, got stuck after less than 2 feet because of unexpectedly hard rock layers. So the liquid water on Mars is real, detected by physics, confirmed by science, and completely unreachable by any tool humanity currently possesses. But what makes this matter beyond just the engineering challenge is what might be living down there. Life on Earth does not require sunlight. That was the assumption for most of human history, but it turned out to be wrong. In the 1970s, scientists discovered entire ecosystems thriving at the bottom of the ocean around hydrothermal vents, where hot water rich in dissolved minerals erupts from cracks in the ocean floor. These ecosystems have no connection to sunlight at all. They run entirely on chemical energy from the Earth's interior. Since then, scientists have found microbial life in the deepest mines on Earth, kilometers underground, living in total darkness, feeding off minerals in the rock and chemical reactions that require no light whatsoever. These organisms are called extremophiles, life forms that thrive in conditions once considered completely hostile to biology. The deep Martian water reservoir has several features that match what extremophiles need: liquid water, geothermal heat from the planet's interior, dissolved minerals from billions of years of contact with rock, chemical gradients where different types of rock meet the water layer. All of these are the kinds of energy sources that sustain underground life on Earth. If life ever got started on Mars during the wet period, 3.5 billion years ago, when the surface had liquid water and a thicker atmosphere, it would have had time to adapt as the planet changed. Life on Earth has survived mass extinctions, ice ages, and asteroid impacts by retreating into protected environments. Microbes retreating underground as Mars dried out is a scenario that matches the general pattern of biological resilience. No one is claiming life is definitely in the Martian water layer. The scientific community is careful about that distinction. The detection of liquid water does not equal detection of life, but the conditions for life, at least the kind of life that does not need sunlight, appear to be present. And the mission profile needed to find out would require drilling 7 to 13 miles through solid Martian rock. That mission does not yet exist. The technology does not yet exist. The funding for that technology does not yet exist. What scientists do know is where to aim. The Shalbatana Vallis region, with its ancient flood channels, its post-flood lake beds, and its connection to the deep geological system, is one of the highest priority targets for future exploration. And the reason that lake beds matter even more than the deep water is something the next part of this story will make very clear. The flood was over. The Northern Ocean was forming. But inside the canyon itself, something quieter was happening. As the main body of floodwater surged northward toward Chryse Planitia, pockets of water got left behind. The floor of Shalbatana Vallis was not perfectly flat. The flood had carved it into an irregular surface of basins, depressions, and lower zones separated by ridges of harder rock. When the main flood moved past, these low spots held water. They could not drain because the terrain around them was higher. They could not evaporate quickly because the atmosphere, while thinning, was still thick enough to slow the process. They became lakes. Scientists identified these ancient lake beds by looking for specific geological signatures in the Mars Express terrain data. The floors of these basins are smooth compared to the surrounding carved rock. Smooth floors in enclosed basins are a classic indicator of lake sediment, fine material that settled slowly through a calm water column over an extended period. The rougher the surrounding terrain, the more clearly the smooth basin floor stands out as a zone where water once sat undisturbed. But the most compelling evidence is the delta formations. A delta forms when a stream or river carrying sediment flows into a standing body of water and slows down. The sediment drops in a fan shape at the point where the moving water meets the still water. On Earth, you can see deltas at the mouths of major rivers, the Mississippi Delta in Louisiana being one of the largest examples. They are distinctive fan-shaped deposits of layered sediment that preserve the exact location of an ancient shoreline. Inside Shalbatana Vallis, scientists found delta formations at multiple points where smaller tributary channels feed into the main valley floor basins. These deltas required two things to form: a source of moving water and a body of standing water to receive it. Their presence inside the canyon confirms that the post-flood lakes were not shallow temporary puddles. They were deep enough, stable enough, and long-lived enough for river systems to develop along their edges and build up significant sediment deposits. Estimating how long these lakes persisted is an active area of research. The thickness of the sediment layers in the basin floors gives a minimum time frame, because sediment accumulates at roughly measurable rates. Current estimates suggest these lakes survived for at least thousands of years, and possibly tens of thousands. Some scientists argue the evidence supports an even longer duration. For a lake to persist that long on Mars, it needed more than just the initial floodwater. It needed a continuous supply of water to replace what evaporated. The most likely source was groundwater seeping slowly through the fractured rock of the canyon walls and floor, feeding the lakes from below, even as evaporation worked against them from above. This is critical because it means the lakes were connected to the deep water system beneath Mars. They were not isolated puddles. They were the surface expression of a much larger underground reservoir, which means anything that lived in those lakes had access to the minerals, heat, and chemical energy of the deep Martian crust. And anything that lived in those lakes, if anything did, left a record in those sediment layers. That record is still there, undisturbed, at the bottom of those ancient basins, waiting. If you wanted to hide a needle, you would choose a haystack. If ancient Martian life wanted to survive, it would have chosen a lake bed. Lake sediment is one of the most protective environments for preserving biological material. When an organism dies in a lake, it sinks to the bottom. If the water is calm and oxygen poor at depth, the organism does not decompose quickly. It gets buried under new layers of sediment, each layer sealing the one below it. Over time, the biological material mineralizes, its organic molecules replaced or stabilized by minerals from the water, creating what scientists call a biosignature, a chemical record that something biological was once present. On Earth, scientists have found preserved biosignatures in lake sediments hundreds of millions of years old. The Apex Chert Formation in Australia contains evidence of microbial life from 3.5 billion years ago, roughly the same age as the Shalbatana Vallis flood. The organisms themselves are gone, but the chemical and structural signatures they left in the sediment are still readable. The lake beds inside Shalbatana Vallis are the same age. They formed in the same geological window as the oldest preserved life on Earth. And on Mars, without plate tectonics to recycle and destroy old rock, without the constant biological activity that churns and disrupts sediment on Earth, those ancient layers are sitting exactly where they were deposited. Plate tectonics is worth pausing on for a moment. Earth constantly recycles its own crust. Old ocean floor dives back into the mantle at subduction zones. Ancient lake beds get folded into mountain ranges, heated, and transformed beyond recognition. The geological record on Earth older than about 4 billion years is essentially gone, destroyed by the planet's own internal recycling system. Mars does not have plate tectonics. Its crust is one solid shell that has not significantly recycled itself in billions of years. A lake bed that formed 3.5 billion years ago on Mars is still a lake bed. The sediment layers are still in order. The minerals deposited by ancient water are still in place. The potential biosignatures from ancient microbes are still preserved in the rock exactly where they settled. This is what makes Mars so scientifically valuable for studying the early history of life. Earth has essentially erased its own oldest records. Mars kept every page. The Perseverance rover, currently operating in Jezero crater, is collecting exactly this type of sediment sample from what scientists believe was an ancient Martian lake. Jezero is estimated to be between 3 and 4 billion years old. The samples Perseverance is collecting will eventually be returned to Earth by a future mission for laboratory analysis. The lake beds of Shalbatana Vallis are in the same age range as Jezero, formed by the same type of geological process, and possibly connected to the same deep water system. A mission targeting the Shalbatana lake sediments would give scientists a second independent data point, a second ancient lake from a different geological context, to compare against whatever Perseverance finds. 2 independent data points from 2 different ancient lakes on Mars. If both show biosignatures, the probability that those signatures are real and not a contamination artifact rises dramatically. The sediment is there, the preservation conditions are right, the age is right. The only thing missing is a rover with the right instruments pointed at the right valley floor. Life does not need sunlight. Mars proved that possibility before we even knew to look for it. On Earth, every ecosystem we once knew about was connected to the star at the center of our solar system. Plants capture its light, animals eat plants. The entire food chain traces back to that one energy source. Scientists assumed this was universal, that life anywhere in the universe would need a star to power it. Then in 1977, a research submersible called Alvin dove into the Pacific Ocean near the Galapagos Islands and found something impossible. At a depth of about 1.5 miles, where sunlight is completely absent and pressure would crush an unprotected human, there were hydrothermal vents on the ocean floor, cracks in the crust where superheated water rich in dissolved minerals was erupting. And around those vents were entire ecosystems, tube worms 8 feet long, clams the size of dinner plates, shrimp clustered in enormous masses, all of them thriving in total darkness, in water hot enough to damage unprotected skin. These ecosystems were powered entirely by chemical energy from the Earth's interior. The heat from the planet's own core was the energy source, not the star above. Scientists named the process that supports these ecosystems chemosynthesis, the production of organic compounds from chemical reactions, rather than light reactions. This discovery fundamentally changed the search for life beyond Earth. Suddenly, life did not need a planet with the right amount of sunlight or the right distance from a star. It needed warmth, liquid water, and dissolved minerals. That description fits the deep interior of Mars almost exactly. The Martian deep water reservoir sits in a zone warmed by the planet's residual geothermal heat. The rock surrounding that water is rich in iron, sulfur, magnesium, and other minerals that support chemosynthetic reactions on Earth. The water itself, having spent billions of years in contact with mineral-rich rock, would carry dissolved compounds that chemosynthetic organisms can use as energy sources. If microbial life established itself in the shallow groundwater system of early Mars, when liquid water was abundant closer to the surface, it would have faced a long, slow reduction in its habitat as the planet dried and cooled. The surface became hostile first. The shallow water layers disappeared next. But the deep zones, buffered by kilometers of rock from the surface environment and warmed from below by the planet's interior, stayed hospitable for far longer. Life retreating into the deep crust as conditions worsen at the surface is a process that happens on Earth too. When environments become extreme, microbes migrate toward the most stable zones available. The most stable zone on Mars for billions of years has been the deep geothermally heated water layer. The timeline matters here. The Shalbatana flood happened 3.5 billion years ago. The deep water detected by seismic instruments is still liquid today. That is 3.5 billion years of continuous liquid water at depth. If life ever adapted to that environment, it has had 3.5 billion years to evolve, specialize, and spread through the underground rock. 3.5 billion years is not a short time. Single-celled life on Earth was already complex and widespread after just that much time. What it means for Mars is something no instrument has yet measured. The flood happened. The scar proves it. The ocean basin confirms it. The chaotic terrain at the origin point marks the exact location. But scientists still argue about what pulled the trigger. Two competing explanations dominate the debate, and both are supported by real evidence. The argument between them reveals how little we still know about the sequence of events that shaped early Mars. The first explanation is a volcanic surge. Early Mars had an extremely active volcanic interior. The massive shield volcanoes in the Tharsis region, the largest volcanic system in the solar system, were growing rapidly during this period. The magma systems feeding those volcanoes extended deep into the planet and generated enormous amounts of geothermal heat. A surge in volcanic activity beneath the Xanthterra region could have rapidly intensified the heating of the underground aquifer, increasing its pressure beyond what the overlying rock could contain. The evidence for this explanation comes from the surrounding geology. The Xanthterra region shows signs of ancient volcanic activity in its rock composition. The lava flows that later filled the Shalbatana Channel suggest an active volcanic system in the area during and after the flood period. A sudden increase in geothermal heat beneath the aquifer fits the timeline. The second explanation is an asteroid impact. A large enough impact in the Xanthterra region could have fractured the overlying rock directly, creating the pathway for the pressurized water to escape. The Orson Welles crater, the flood's origin point, is an impact crater. If a later, smaller impact struck in the right location and cracked the already stressed rock above the aquifer, it could have opened the seal. The evidence for this explanation is the location of the chaotic terrain inside the crater basin itself. Impact craters have pre-fractured floors. A subsequent impact, or even a seismic event from a distant impact, could have triggered failure in a crater floor already weakened by the original impact event. Some researchers argue for a combined explanation. The original impact that created the Orson Welles crater fractured the crust. Millions of years later, a volcanic surge heated the aquifer below the fractured zone. The weakened rock, already compromised by the impact, finally gave way under the increased pressure. What scientists agree on is the result. The trigger, whatever it was, released a volume of water and created a channel that is 800 miles long, 6 miles wide, and over 1,600 feet deep in places. The trigger itself is almost irrelevant compared to what followed, but understanding the trigger matters for predicting where other flood channels might be hidden on Mars, and where other aquifer systems might have released, and where they might still exist underground. Every candidate trigger location, every fractured crater basin above a possible aquifer zone, every region with both ancient impact scars and signs of geothermal activity becomes a candidate for the same kind of discovery. Mars may have more scars like this one. Smaller ones, larger ones, different ages. The Shalbatana Vallis discovery opened a question that extends far beyond this single channel. How many times did Mars flood itself from the inside? The flood lasted days to weeks. The lakes lasted much longer. After the main surge of water carved through the channel and poured into Chryse Planitia, the smaller pockets of water left behind in the valley basins began a slower story. These lakes did not drain away instantly. They sat, fed by slow seepage from the fractured rock around them. shrinking gradually as evaporation and the thinning atmosphere worked against them. Figuring out exactly how long they survived requires reading the geological record very carefully. The primary tool is sediment thickness. Scientists estimate how quickly sediment accumulates in a body of standing water by measuring the grain size of the particles, their mineral composition, and the rate at which similar minerals settle in laboratory conditions. By measuring the thickness of the lake sediment layers in the Shalbatana basin floors and dividing by the estimated accumulation rate, they can calculate a minimum duration for each lake. Current estimates, based on the sediment data available from orbital imaging, suggest the post-flood lakes survived for at least several thousand years. Some individual basins show sediment layers thick enough to suggest tens of thousands of years of accumulation. A small number of scientists working with the upper range of sediment thickness estimates argue for even longer durations, potentially hundreds of thousands of years for some of the deeper, more sheltered basins. The delta formations add another constraint. Deltas require sustained water flow from tributary channels. A delta does not build up in a single season. The deltas found at the edges of the Shalbatana lake basins have measurable volume, and calculating how long it takes for a stream of the estimated size to deposit that volume of material gives a minimum time frame for the lake's existence. The result from the delta calculations broadly matches the sediment calculations. These lakes were persistent. They were stable enough for long enough to develop their own miniature drainage systems and accumulate their own sediment records. What ended them is where the story becomes sobering. Mars's atmospheric pressure was already declining during this period. Every 1,000 years, the pressure dropped a little more. The temperature range at the surface widened as the greenhouse effect weakened. Seasons became more extreme, and as the pressure approached the critical threshold, where liquid water can no longer exist at the surface, the lakes entered their final phase. They did not drain. The valleys around them had no outlet to the broader terrain. They evaporated. As the water level dropped, mineral concentration in the lake water increased. The lakes became saltier and more chemically extreme as they shrank. Eventually, the remaining water reached a concentration where it could persist at lower temperatures than fresh water, extending the lake's life a little longer. Then even that ended. The water converted to ice, and the ice slowly sublimated into the thinning atmosphere and was carried away. What was left behind was the sediment, perfectly layered, perfectly preserved, a geological archive of everything that happened in those lakes, from the first day they formed to the last day the water disappeared. The question of whether something biological is recorded in those layers is one that only a physical sample can answer, and the mission to collect that sample is not yet funded or launched. The lakes existed. The sediment proves it. The deltas confirm it. But there is a troubling question sitting beneath all of that evidence. By the time those lakes formed, 3.5 billion years ago, how much sky did Mars still have? The atmosphere of early Mars is one of the most actively debated topics in planetary science. Scientists know what Mars's atmosphere looks like today: thin, cold, mostly carbon dioxide, with a surface pressure less than 1% of Earth's. They know the planet had a thicker atmosphere billions of years ago, but pinning down exactly how thick that atmosphere was at any specific moment in Martian history is genuinely difficult. The problem is that the evidence cuts in two directions at once. On one side, the existence of the flood, the lake basins, the delta formations, and the sediment layers all require liquid water at the surface. Liquid water on the Martian surface requires a certain minimum atmospheric pressure. You cannot have those geological features without the conditions that created them. So the atmosphere must have been thick enough to support liquid water at the time these features formed. On the other side, models of how fast Mars lost its atmosphere after its magnetic field shut down suggest the erosion rate was high. If those models are correct, the atmosphere may have already thinned significantly by 3.5 billion years ago. Some models place the atmospheric pressure at that time at just a few % of Earth's current pressure, barely enough to keep water liquid at the temperatures Mars would have experienced. At a few percent of Earth's pressure, liquid water can exist on Mars, but only in narrow temperature and elevation conditions. It would be unstable. It would evaporate quickly. The kind of long-lived, stable lakes that the sediment evidence suggests would be very difficult to explain under a thin atmosphere scenario. This tension in the data drives a lot of current research. Scientists building climate models for ancient Mars are trying to find a set of conditions that can explain both the atmospheric erosion rate and the clear geological evidence for sustained liquid water. Some propose that volcanism was pumping carbon dioxide and water vapor into the atmosphere fast enough to partially offset the loss. Others suggest that impacts from asteroids and comets periodically delivered new atmospheric gases and temporarily thickened the sky. A third group argues that the lakes were not open-air features at all. They propose that ice covered the surface of the lakes for most of the year, insulating the liquid water below. Under an ice lid, water can remain liquid even in thin atmosphere, low-temperature conditions. The sediment patterns under this scenario would look similar to what scientists actually observe in the basin floors. The answer matters enormously for the life question. An open-air lake with sunlight reaching the water surface is one type of environment. A permanently ice-covered lake in the dark is a very different one. Each supports different types of potential biology, with different preservation patterns in the sediment. The sediment layers inside the Shalbatana basins might actually contain the answer. The specific mineral types that form in ice-covered lakes versus open lakes are different. Measuring those minerals directly from a sample could resolve the debate, but that sample has not been collected yet. Liquid water, 7 to 13 miles underground, warmed by geothermal heat, rich in dissolved minerals, isolated from radiation, sitting in porous rock that could shelter microbial communities. The question is blunt: is something alive down there? Scientists are careful with their language here. The detection of liquid water does not mean the detection of life. Water is necessary for life as we know it, but water alone does not produce life. The conditions that support life are present in the Martian deep crust. Whether those conditions are sufficient and whether life ever actually got started there are separate questions. The most optimistic scenario goes like this. Life got started on Mars during the wet period, between 4 and 3.5 billion years ago, when surface water was abundant and conditions were broadly similar to early Earth. Microbial life, simple single-celled organisms, established itself in shallow groundwater and surface lakes. As conditions worsened, the surface life died off. But microbial communities in the shallow underground zones retreated deeper, following the water as it migrated downward. Over billions of years, they adapted to the deep, dark, mineral-rich environment. Their descendants are still there, living in the pore spaces of deep Martian rock, metabolizing mineral compounds, reproducing slowly in the cold and dark. The most conservative scenario is simpler. Life never got started on Mars. The chemistry needed to jump from complex organic molecules to self-replicating life did not occur. The water was there, the conditions were there, but the specific sequence of events that produces biology from chemistry never happened on Mars. The deep water is just water. Both scenarios are entirely consistent with what science currently knows. The detection of liquid water does not favor one over the other. What would help distinguish them is a measurement of the chemistry of that deep water. Certain organic compounds, specific ratios of carbon and nitrogen isotopes, and particular types of mineral alteration patterns are associated with biological activity on Earth. If instruments could sample the deep Martian water and find those signatures, it would strongly suggest biological activity. If the water showed no biological chemistry signatures at all, it would lean toward the lifeless scenario. But reaching the water requires drilling 7 to 13 miles through hard Martian rock, and every other challenge of Mars exploration, the distance, the communication delay, the dust, the radiation, the temperature extremes, all apply on top of that drilling requirement? The honest answer is that no one knows what is in that deep reservoir. The physics confirms the water is there. The chemistry of what is dissolved in it is unknown. Whether anything is swimming in it, or floating in it, or adhering to the walls of the rock pores it fills, is genuinely undetermined. That uncertainty is significant. Mars is the closest planet to Earth with confirmed liquid water. The deep Martian reservoir is the most accessible known body of extraterrestrial liquid water in the solar system. Whatever answer that water holds has implications that stretch far beyond Mars, and the technology gap between what we know and what we can actually measure is closing. Slowly. 13 miles of rock. That number sits between humanity and the answer to one of the most important questions ever asked. Is there life beyond Earth? And the barrier is not a mystery or a philosophical problem. It is an engineering one. We simply do not have a drill that can reach that depth on another planet. To understand why this is so difficult, start with what drilling on Earth actually requires. The Kola Superdeep borehole, drilled in Russia starting in 1970, is the deepest hole humans have ever made on any planet. It took 24 years to complete. It required a drilling rig the size of a building, constant replacement of drill bits that wore out under extreme heat and pressure, massive amounts of drilling fluid pumped down continuously to keep the borehole from collapsing, and a team of engineers working around the clock for more than 2 decades. The final depth was about 7.5 miles. The project stopped because the heat at the bottom destroyed every drill bit within hours of reaching that depth. The rock at that depth was hotter than 350 degrees Fahrenheit and under pressures that made it behave almost like a plastic material rather than solid rock. Drilling through it became physically impossible with the technology available. Now add the conditions of Mars. Every piece of equipment sent to Mars has to survive a 7-month journey through space, arrive safely using a parachute and rockets, and then operate autonomously because the communication delay between Earth and Mars is between 3 and 22 minutes. One way. Engineers cannot issue real-time commands. Every decision the drilling system makes has to be pre-programmed or handled by onboard computer logic. The drilling rig would have to be compact enough to land on Mars, robust enough to survive the landing, and capable of operating for years in a temperature environment that swings between positive 70 and negative 195 degrees Fahrenheit in a single day in some regions. The power required for deep drilling is enormous. Current Mars missions run on solar panels or small nuclear batteries. Neither generates anywhere close to the power needed for a 7 to 13-mile drilling operation. Scientists are aware of all of this. The path toward a deep drilling Mars mission runs through several intermediate steps. First, developing deep drilling technology on Earth that works in extreme heat and pressure without a human crew managing it. Second, miniaturizing that technology enough to fit inside a Mars spacecraft. Third, developing a power source capable of sustaining the operation for the years it would require. None of these problems are considered impossible. They are engineering challenges, and engineering challenges get solved when enough resources and attention are directed at them. The question is how much priority the scientific community and the agencies that fund space exploration choose to assign to this specific mission type. The discovery of the deep Martian water reservoir in 2024 substantially elevated the urgency of that priority question. Before that seismic data was published, the deep crust of Mars was considered a speculative target. After the data, it became a confirmed location of liquid water. The argument for prioritizing a deep drilling mission became significantly stronger. The counter-argument is cost, timescale, and the availability of other high-value targets that are more immediately accessible. The decision of where to focus is being made right now. Every Mars mission so far has looked at the surface. Rovers drive across rock. Landers dig a few inches into the soil. Orbiters scan from above. The entire history of Mars exploration, from Viking 1 in 1976 to Perseverance today, has been conducted within the first few feet of the Martian surface. The discovery of liquid water at depth and the evidence for ancient lake beds in the Shalbatana region suggest that the most important targets are not at the surface at all. Future missions aiming to answer the life question will need to do something Mars exploration has never done: go deep. The first step does not require drilling 13 miles. It requires something far more achievable: drilling just a few hundred feet deep enough to get below the thin radiation-damaged surface layer and into protected rock where organic molecules are not constantly destroyed by cosmic rays. Mars has no magnetic field and almost no atmosphere to block radiation. Cosmic rays hit the surface continuously and penetrate the top few feet of rock, breaking apart complex organic molecules that might otherwise be preserved. Biosignatures that would be readable 5 or 6 feet down might be completely destroyed at the surface. Every rover that has sampled rock from the Martian surface has been analyzing material that has been radiation processed for billions of years. A mission with a drill capable of reaching just a few hundred feet could access rock that has been shielded from cosmic rays by the overlying material. In those protected layers, organic chemistry would be preserved much closer to its original state. A drilling mission targeting the sediment layers in the Shalbatana Valley basins, going deep enough to pass through the radiation zone and into the protected sediment, would give scientists their first clean look at ancient Martian chemistry. The next step beyond that would be a seismic monitoring network. Placing multiple seismometers across the Martian surface, rather than the single InSight instrument, would allow scientists to triangulate the exact depth, thickness, and lateral extent of the deep water layer with much greater precision. They could map where the reservoir is largest, where the rock above it is thinnest, and where a future drilling mission would have the best chance of reaching it with the shortest possible drill depth. Mission planners are also thinking about alternative approaches to reaching deep water without drilling straight down. One concept involves targeting areas where ancient geological faulting may have brought deep rock closer to the surface. If the deep water layer has been uplifted by tectonic stress in certain regions, a borehole in those areas might reach the water at a shallower depth than 13 miles. Another concept involves looking for locations where the deep water naturally reaches the surface through faults or fractures. Similar to springs on Earth, orbital spectrometers have found hydrated minerals in some locations that could indicate past or current water upwelling. If those locations can be confirmed as active seeps, a surface mission could sample the water without any drilling at all. Each of these approaches requires a different mission profile, different instruments, and different landing targets. Planning any of them starts with a detailed map of the Martian subsurface that does not yet exist. Building that map is the next essential step, and it starts with listening to the planet shake. Mars was supposed to be the easy answer. It is the closest planet. It has a surface that rovers can drive on. Scientists have sent dozens of missions there. If life exists anywhere beyond Earth in our solar system, Mars was always the first candidate on the list. For decades, that search focused on the surface. Did Mars ever have water? Did it ever have a warm enough climate? The answers are yes and yes, but the surface gave up its water long ago, and any life that existed there would have died with it. The discovery of liquid water still present deep inside Mars changes the time frame of the question dramatically. Before the seismic data, the window for life on Mars was ancient. Life might have existed billions of years ago in the warm, wet period, and then gone extinct when the conditions disappeared. The search was essentially archaeological, looking for fossils and chemical remnants of something long dead. After the seismic data, the window is open right now. The conditions for life are present on Mars today, not just in the geological past. Any life that survived the transition from the wet surface period to the deep underground environment would still be alive. The question moved from past tense to present tense. This is a significant shift. Finding fossil evidence of ancient life would be scientifically extraordinary. It would confirm that life arose independently on 2 planets in the same solar system, which would have profound implications for how common life is across the universe. But finding active living biology on Mars would be something categorically different. It would mean life is happening on two planets in our solar system simultaneously. The probability of life existing throughout the galaxy would increase enormously. The Shaalbatana Vallis discovery fits into this broader picture because it connects the ancient surface water story to the deep underground water story through a single geological system. The flood brought surface water deep into the crust through the chaotic terrain. The lake beds gave surface life time to adapt to shallow underground conditions. The deep water reservoir provided the final refuge as the surface environment collapsed. If life made that journey, the Shaalbatana region is where the clearest evidence of the transition would be found. The sediment layers record the surface period. The deep water holds whatever survived. The implications extend beyond Mars. Europa, one of the moons of Jupiter, has a confirmed liquid water ocean beneath its icy surface, kept liquid by tidal heating from Jupiter's gravity. Enceladus, a moon of Saturn, actively sprays water vapor from cracks in its south pole, confirmed to contain organic molecules and hydrogen, both associated with the chemical reactions that support life on Earth. Mars is the simplest case. It has solid ground, a history humans understand in detail, and instrumentation already in place. If scientists can develop the tools to answer the life question on Mars, those same tools and that same knowledge base will apply directly to Europa and Enceladus. Mars is the proving ground. What we learn there scales outward. 2 data points change everything. Right now, humanity has one confirmed example of life in the universe: Earth. With one example, you cannot draw a conclusion about how common life is. Maybe Earth is a miracle, a 1 in a trillion accident that produced biology from chemistry. Maybe life arises whenever conditions are right. With one example, both possibilities are equally supported by the evidence. Finding life on Mars, even a microbial life, even a single living cell in a sample of deep rock, would give science its second data point. And a second data point in the same solar system, orbiting the same star on the neighboring planet, would be one of the most statistically significant discoveries in human history. Here is why. If life arose independently on both Earth and Mars, given that both planets formed from the same cloud of material around the same star at roughly the same time, then life is apparently something that happens easily when conditions allow it. The process of chemistry becoming biology would be a natural consequence of the right environment, not a vanishingly rare accident. The Milky Way galaxy contains an estimated 200 billion to 400 billion stars. Astronomers have confirmed that most stars host at least one planet. Many of those planets sit in zones where liquid water could exist. If life arises easily given the right conditions, and Mars proves that 2 out of 2 rocky planets in one solar system develop life, then the probability of life existing across the galaxy becomes very high. The counterargument is panspermia, the hypothesis that life on Mars and life on Earth might actually share a common origin. When large asteroids or comets hit a planet hard enough, they can eject material into space at escape velocity. That material, traveling through space, can eventually land on other planets. Microbes embedded in rocks have been shown to survive the vacuum of space for extended periods. If a rock carrying ancient Earth microbes landed on Mars and seeded life there, or vice versa, then finding life on Mars would not be evidence of an independent origin. Scientists are aware of this complication. Distinguishing between shared origin and independent origin Mars life would require detailed analysis of the biochemistry of any discovered organisms. If Martian life uses the same genetic code, the same amino acid handedness, and the same basic molecular machinery as Earth life, shared origin would be strongly suspected. If the biochemistry is fundamentally different, independent origin would be the conclusion. Either outcome is remarkable. Shared origin would confirm that life can travel between planets on rocks and colonize new worlds, turning the entire solar system into a connected biological system. Independent origin would confirm that life is a natural outcome of chemistry in the right conditions, making a living galaxy overwhelmingly probable. The question begins at Shelbatana. The scar that the flood left on Mars connects directly to the deepest, most important question the species examining it has ever asked. And the answer is sitting, right now, in rock and water, 7 to 13 miles underground, on a red planet, 40 million miles away. Mars did not always look the way it does today. 4 billion years ago, the planet was a different world. Its atmosphere was thicker, its magnetic field was active, and its surface held liquid water in rivers, lakes, and possibly a vast northern ocean. Volcanic systems were erupting continuously, pumping gases into the air and heat into the crust. The planet was geologically alive in a way that Earth still is today. The trajectory from that world to the frozen desert of modern Mars is one of the most dramatic planetary transformations in the solar system, and understanding it tells us something important about how fragile habitable conditions actually are. The collapse began with the magnetic field. Around 4 billion years ago, Mars's iron core had cooled enough that the convection currents driving the magnetic field began to weaken. Without those currents, the field faded. Within a relatively short geological window, the protective magnetic bubble surrounding Mars shrank and vanished. The solar wind arrived at the upper atmosphere without obstruction. The atmosphere began to thin, not all at once, but steadily year after year, at a rate that climate models now estimate at roughly 100 grams of atmosphere lost per second, averaged over the long term. That sounds small. Across millions of years, it adds up to most of an atmosphere. 3.5 billion years ago, right at the moment of the Shelbatana flood, Mars was in transition. The magnetic field was gone. The atmosphere was thinning but still substantial enough to support surface liquid water. The internal heat driving geothermal activity and volcanism was still significant. This is the period the new images illuminate most clearly. After the flood, the decline accelerated. The atmosphere crossed below critical pressure thresholds. Surface water became increasingly unstable. By 3 billion years ago, liquid water could no longer persist on the Martian surface under normal conditions. The Northern Ocean had evaporated. The lake beds had dried. The surface was frozen and irradiated. The interior stayed warmer longer. Volcanic activity continued on a reduced scale for billions of years after the surface froze. Olympus Mons and the other Tharsis volcanoes may have had eruptions within the last few 100 million years, geologically recent by any measure. The deep geothermal heat that kept the underground water liquid has been declining slowly, not suddenly. Today, Mars is at a specific point in that long decline. The surface is dead, the upper crust is frozen and irradiated. The deep crust still contains liquid water, warmed by fading geothermal heat. That heat will continue to decrease as the planet's interior cools further. At some point in the very distant future, even the deep water will freeze. Mars is in its late period. The habitable zone has contracted entirely underground, and it is contracting further with every million years that passes. Humanity arrived at the moment when the underground habitable zone still exists, when the seismic instruments exist to detect it, and when the scientific understanding exists to interpret what those instruments find. The timing of this discovery is not accidental. It is the result of decades of missions building on each other. But this timeline raises a question that brings the story much closer to home. Earth is not immune to what happened to Mars. The same process that stripped Mars of its atmosphere, the loss of a protective magnetic field, is theoretically possible on Earth. Our planet's magnetic field is generated by convection currents in the liquid iron outer core. Those currents depend on the temperature difference between the hot inner core and the surrounding mantle. As Earth cools over billions of years, that temperature difference will slowly decrease, eventually weakening the convection currents and reducing the strength of the magnetic field. This will not happen tomorrow. The timescale is billions of years, but the physics that produced a dead Mars is built into Earth as well. There is also a shorter-term instability to consider. Earth's magnetic field is already showing signs of change. The magnetic North Pole has been drifting towards Siberia at an accelerating rate over the past few decades. The overall strength of the field has decreased by about 9% over the last 150 years. Scientists debate whether this represents a long-term trend or a normal fluctuation, but the movement is measurable and real. Earth's magnetic field reverses polarity periodically. North becomes south, and south becomes north. The geological record shows these reversals have happened hundreds of times in Earth's history. During a reversal, the field weakens significantly before reforming in the opposite direction. The transition period can last thousands of years. During a reversal, the protection the field provides against the solar wind decreases substantially. Auroras appear at lower latitudes. Cosmic radiation reaching the surface increases. Satellites and electrical grids face disruption. The last full reversal happened roughly 780,000 years ago. Based on the geological record, another one is statistically overdue. A reversal would not strip Earth's atmosphere the way Mars's permanent field loss did. Earth's field has always reformed, but it illustrates that the boundary between a magnetically protected planet and an unprotected one is not as fixed as daily life makes it seem. The Martian story also has a more immediate lesson for Earth's water. Most of Earth's water sits on the surface and in the upper crust, exposed to the climate system. If Earth lost a significant portion of its atmosphere for any reason, volcanic outgassing insufficient to replenish it, a catastrophic impact, or a prolonged reduction in magnetic shielding, surface water would begin to escape into space. The process would be slow by human timescales, but irreversible on geological ones. Mars's northern ocean did not drain into the ground. It evaporated into space. Once atmospheric water vapor reaches the upper atmosphere and gets hit by solar wind, it is gone permanently. Earth's oceans could follow the same path, given the right conditions and enough time. Studying Mars is not just archaeology. It is the most detailed example available of what happens to a planet when its protective systems fail. Every measurement scientists take of the Shalbatana flood, the ancient ocean, the deep water, and the atmospheric collapse is a data point in a model that also applies to Earth. The better we understand how Mars lost everything, the better equipped we are to recognize if Earth starts on the same path. Every rock layer in the walls of Shalbatana Vallis is a chapter in a book. The flood exposed those layers when it carved the canyon walls. Before the flood, these rock sequences were buried, stacked in sequence underground, invisible. The rushing water peeled back the surface terrain like a blade, leaving a cross-section of Martian history exposed from top to bottom along 1,600 feet of canyon wall. Reading those layers from the bottom up is reading Mars backward in time. The deepest layers are the oldest, rock formed in the earliest period of Martian history. Moving upward through the wall, each layer represents a more recent period of geological activity. The topmost layers are the most recent before the flood carved them into visibility. Geologists call this principle of reading rock layers stratigraphy. On Earth, stratigraphy is complicated by plate tectonics, which folds, disrupts, and overturns rock sequences. On Mars, without plate tectonics, the layers are almost entirely undisturbed. They sit exactly in the order they were deposited, oldest at the bottom, newest at the top. The Mars Express camera captured high-resolution spectral data from the canyon walls, identifying the mineral composition of each visible layer. Different minerals form under different conditions. Olivine forms in volcanic environments. Clay minerals form where water interacts with rock over long periods. Sulfate minerals form where water evaporates and concentrates. Carbonate minerals form in water with specific chemistry. The spectral data from the Shalbatana walls shows a sequence that matches the known history of Mars. The deepest ancient layers contain minerals consistent with the earliest volcanic period. Above those, Clay minerals indicate a period when water was interacting with the rock. Above the clays, sulfate minerals mark the transition to a drier, more acidic environment as water was leaving. The sequence tells the same story as the broader Martian timeline, confirmed independently by the chemistry of the canyon walls. This kind of cross-check is important. The geological story of Mars has been assembled from many different data sources: orbital imaging, rover chemistry measurements, meteorite analysis, and climate models. When the stratigraphy of a newly exposed canyon wall matches predictions from those other sources independently, it confirms that scientists have the basic story right. But there are also surprises in the wall data. Some layers show mineral combinations that are unexpected, mixtures of compounds that do not easily fit the standard model of how those minerals form. These anomalies are the targets of ongoing research. Unexpected chemistry in ancient rock layers is exactly the kind of signal that might indicate unusual processes, including biological ones. On Earth, ancient microbial activity leaves specific chemical fingerprints in the rock layers it inhabits. Iron oxidation patterns, carbon isotope ratios, and specific sulfur compounds can all indicate biological processing rather than purely geological chemistry. Scientists are looking for analogous patterns in the Shalbatana wall data. The canyon walls are open, exposed, and readable from orbit. No rover has driven their length. No instrument has been placed against those layers to measure them directly. Everything known about their chemistry comes from light reflected off their surface and captured by a camera 200 miles above. Direct contact would tell a far more detailed story. A robot parked against one of those canyon walls, pressing instruments directly against the rock face, would have access to measurements that orbital imaging cannot provide. That robot does not yet exist. Everything the new images revealed is pointing scientists toward a specific decision. Where do we send the next mission? Mars already has active operations. Perseverance is in Jezero Crater, drilling core samples and caching them for eventual return to Earth. Curiosity is still operating in Gale Crater, analyzing rock chemistry and monitoring weather. The European Space Agency's Trace Gas Orbiter is scanning the atmosphere for chemical signatures. None of them are anywhere near Shalbatana Vallis. The Shalbatana region, based on the May 2026 images and the deep water detection from seismic data, is now one of the highest priority locations for future Mars exploration. Scientists have identified several specific targets within and around the channel that would yield the most scientific return. The first target is the chaotic terrain at the Orson Welles crater origin point. This zone, where the flood began, contains the most direct evidence of the ancient groundwater system. Sampling the collapsed block terrain would give scientists rock from deep in the ancient crust. Brought to the surface by the collapse, those samples could be dated precisely, identifying the exact age of the aquifer system and the flood event. The second target is the ancient lakebed sediments and the valley basins. These sediment layers, identified by smooth basin floors and delta formations, are the primary biosignature target. A rover capable of drilling a few hundred feet into the sediment below the cosmic radiation zone could extract samples from the most protected and preserved layers. Those samples, returned to Earth, would be subjected to the most sensitive chemical analysis available in modern laboratories. The third target is the boundary zone where the Shalbatana Channel meets Chryse Planitia. This is where the ocean sediment meets the flood deposit, where the chemistry of two different water bodies mixed. The mineral signatures at this boundary could reveal detailed information about the composition of both the floodwater and the ancient ocean. Landing in the Shalbatana region presents engineering challenges. The terrain is complex, with steep walls, boulder fields, and elevation changes that make navigation difficult for current rover designs. The canyon floor, while flatter, requires a landing system capable of precise targeting in an enclosed space. None of these challenges are insurmountable. They are exactly the kind of engineering problems that Mars mission planners are trained to solve. The scientific return justifies the investment. The window for planning the next generation of Mars missions is open right now. Proposals are being submitted. Mission concepts are being evaluated. The discovery of the deep-water reservoir elevated the priority of subsurface exploration dramatically. The Shaalbatana images released in 2026 elevated the priority of this specific region. The decisions being made in the next few years about which missions get funded, which landing sites get selected, will determine how quickly humanity can answer the question that this entire canyon, this entire flood, this entire planet's geological history is building toward. Is Mars alive, or was it ever 800 miles of carved rock, an ancient ocean, lake beds preserved in perfect order, liquid water still sitting 7 miles underground? All of it points toward one question that science has not yet answered. Was Mars ever alive? The evidence for conditions that could support life is strong. The ancient surface water lasted long enough for lake systems to develop. The post-flood lakes persisted for thousands to potentially hundreds of thousands of years. The deep underground water has existed continuously for over 3 billion years, kept liquid by geothermal heat, rich with dissolved minerals, isolated from the radiation and cold of the surface. On Earth, life arose roughly 4 billion years ago, around the same time Mars had its most favorable surface conditions. The chemistry that drove early life on Earth, liquid water, chemical energy sources, mineral-rich environments, was present on Mars at the same time. There is no known scientific reason why life could not have started on Mars during that window. But knowing that life could have started is very different from knowing that it did. The jump from chemistry to biology, from complex organic molecules to a self-replicating system, is the one step in the history of life that scientists least understand. It happened on Earth. Whether it happened on Mars is the question. And the honest scientific answer, in the year 2026, is that we do not know. What we know is where to look. The Shaalbatama Vallis region holds a layered geological archive of the most critical period in Martian history. The sediment layers in the ancient lake basins date to exactly the window when life, if it ever existed, was most likely present. The canyon walls expose chemical sequences that no other location on Mars has revealed in this level of detail. The chaotic terrain at the origin point contains rock from deep in the ancient crust, brought to the surface where instruments can potentially reach it. The deep water, detected by seismic instruments, is the wild card. It represents the possibility that whatever happened to Martian biology 3.5 billion years ago is still happening, underground, right now. Living biology in a confirmed liquid water reservoir on another planet would be the most significant discovery in human history. It would permanently change how humanity understands its place in the universe. The scar that the flood left on Mars is a geological record of catastrophe, a planet that lost its sky, lost its oceans, lost its warmth, and retreated into itself. But it is also something else. It is a map of where the water went, where the chemistry was preserved, and where the search for life beyond Earth should focus next. The flood happened 3.5 billion years ago, and nobody was watching. Today we have instruments that can read the aftermath. Tomorrow, we might have instruments that can sample it. And in the generation after that, we might have the answer. Mars has been hiding something enormous. The images proved it. The seismic data confirmed it. The lake beds, the sediment, the ash patch, the Mesa Islands, the carved walls, the deep water, they all point in the same direction. Dig deeper. Go further. Do not stop asking. The answer is in there somewhere. And the valley is waiting.